66 million years ago, a predator bigger than a city bus roamed North America. You've heard its name, Tyrannosaurus Rex. But forget the movies for a second. This was a real animal, a creature built for a world very different from ours. Yet, what if this giant suddenly appeared today? Could something that colossal, powerful, and prehistoric adapt and thrive in our world of highways, skyscrapers, and social media? The atmosphere now might leave a T-Rex gasping for air. Some studies suggest that late Cretaceous air had higher oxygen, possibly up to 30 to 35% than today's 21%. Dropping a T-Rex into our thinner air would feel like placing it at a high altitude, as if it was at the base camp of Everest. According to one zoologist, a modern T-Rex might need a more efficient respiratory system. Fortunately, many theropod dinosaurs had bird-like lungs with air sacs, which are highly efficient. Those could give T-Rex a fighting chance. Over time, it might also adapt by lowering its metabolism or activity level to use oxygen more sparingly. A slower pace of life and more rest between hunts could become its new normal in an oxygen-poor world. T-Rex evolved in a warmer world than ours. Global temperatures in the late Cretaceous were about 4 degrees Celsius higher than today on average, and there were no freezing winters in its range. Our modern climate would impose cooler seasons and even cold nights that T-Rex never experienced. How to adapt? It might seek out tropical equatorial regions where the heat and humidity still resemble its ancient home. If forced into cooler climates, T-Rex could face trouble. Unlike furry animals, it wasn't built for the cold. Fossil skin impressions tell us adult T-Rexes were mostly scaly, not fully feathered. They likely didn't have a thick insulation layer. A modern T-Rex might grow a bit of fluffy covering if it had generations to evolve, similar to how some of its smaller cousins had feathery coats. But a sudden appearance in a cold environment would leave it shivering. Being giant was an advantage in the Cretaceous, but in today's world, it could be a handicap. At 8+ tons, a T-Rex would require a tremendous amount of food to sustain itself. Modern ecosystems have fewer gigantic prey animals. With scarcer food, natural selection might favor a somewhat smaller, leaner T-Rex over time. Paleontologists speculate that if the T-Rex lineage had continued, it might have either grown smaller and faster, or even larger and more efficient, depending on pressures. In a food-limited scenario, a downsized, modern T-Rex would have better odds. Along with size adjustments, it might need to store fat or endure long periods without eating, much like crocodiles or Komodo dragons do. Research suggests it was not a sprinter, perhaps reaching speeds of 20 to 25 kilometers an hour, around 12 to 15 miles per hour at best. That's slower than a galloping horse or deer, but still faster than a human can run. In modern habitats, many prey animals are swift. A T-Rex might not bother trying to outrun the fastest gazelles. Instead, it would adapt its hunting style. Expect a T-Rex to rely more on stealth and ambush, using cover to get close, than attacking with a sudden burst of speed. Its powerful legs could still accelerate it quickly over a short distance, enough to surprise a large target. Over evolutionary time, perhaps natural selection would favor individuals with slightly longer legs or more muscular builds for speed, or conversely, those that are more energy-efficient walkers. But even without major changes, a modern T-Rex would still be a capable mover for its size. It could likely trek long distances in search of food, maintaining a steady pace. Tyrannosaurus rex lived in a humid, subtropical habitat during the late Cretaceous. Fossils from the Hell Creek Formation show that its environment was a low-lying floodplain, dotted with rivers, swamps, and forested regions. Think of lush conifer forests mixed with palm trees and ferns, a landscape with warm temperatures year-round and abundant rainfall. Fast forward to today, that Cretaceous habitat is gone. Mountains have risen, sea levels dropped, and the climate has cooled. If T-Rex were to survive now, it would seek out the closest match to its old home. The good news is that parts of our planet still offer warm, lush conditions reminiscent of the late Cretaceous. Experts note that land dinosaurs would find tropical and subtropical regions quite comfortable climate-wise. A large marshy region like the Everglades in Florida or the Pantanal in Brazil is steamy and full of life. Such places have broad rivers, muddy banks, and tall reeds, somewhat like a mini version of Hell Creek's environment. However, today's wetlands mostly have smaller creatures. The lack of huge land prey is a downside, though a T-Rex might snack on the abundant alligators or wild pigs in these areas. Rainforests are warm enough, but their dense jungle might be challenging for a creature the size of T-Rex. Also, big ground-dwelling prey is relatively scarce in deep rainforests. You won't find herds of giant herbivores in the heart of the Amazon like you had in Hell Creek. T-Rex might instead patrol the edges of forests and open clearings. The African savanna is in many ways an ideal stand-in for the late Cretaceous plains. Think of the Serengeti or Okavango region. Expansive grasslands dotted with groves of trees, a warm climate with a wet and dry season, and crucially, herds of large herbivores. This is perhaps the closest modern equivalent to the world of T-Rex. A T-Rex could feel at home under the African sun, moving between patches of acacia trees and stalking prey across open plains. We'll discuss the prey in a moment, but from a habitat standpoint, a protected savanna or broad grassland might be the best place for a T-Rex to thrive today. A 65 million year leap in time would force T-Rex to adjust its menu. In the Cretaceous, it feasted on giant plant-eating dinosaurs. Today, those are long gone. So, what could replace them as prey? Likely the biggest herbivores available, similar in mass to its dinosaur prey. In an African savanna scenario, we would expect elephants, rhinoceroses, hippos, Cape buffalo, giraffes. An adult elephant is comparable in size to a triceratops or edmontosaurus. Taking down such massive prey would be perilous even for a T-Rex. Just as lion prides today target elephants or giraffes with mixed success, a lone T-Rex would have to be strategic. It might prefer juvenile or weakened individuals. For example, a young elephant separated from the herd or an old, sick giraffe lagging. Its attack would be brutal, a charging hit to knock the prey off balance, followed by crushing bites to critical areas. The T-Rex's bite force could crush through an elephant's leg bone or a rhino's thick hide. One or two well-placed bites might mortally wound even the largest mammal. Still, an elephant can fight back. A swing of its trunk or tusks could injure the T-Rex. We might see behavior similar to what T-Rex likely did with Triceratops. Target the less dangerous flank or rear, avoid those tusks or horns, and let the prey weaken from blood loss. Over generations, if hunting large, dangerous game became routine, natural selection might favor more intelligent hunting tactics or even social hunting. Outside Africa, a T-Rex might look to other regions. In South Asia, elephants and water buffalo could be targets. In Southeast Asia, perhaps large bovines like gaur or the last remaining rhinos. In North America, wild bison or moose would be among the largest land animals. But a T-Rex might need to make do with multiple smaller kills. It could also prey on horses or cattle on ranch land, which would undoubtedly cause conflict with humans. In South America or Australia, native megafauna are largely gone. These might not satisfy its huge appetite unless it ate many of them. Thus, the highest likelihood of sufficient prey biomass is again in Africa, or possibly parts of Southeast Asia. A hungry T-Rex is not going to be very fussy. We know from fossil evidence it could scavenge carcasses. In modern times, it would continue this behavior. It might trail behind vulture flocks or watch where lions and hyenas gather, then scare them off and claim the carcass. Its arrival would send any other predator running. Even a pride of lions would likely retreat from a feeding T-Rex rather than risk death. This means it could steal kills and subsist partly as a scavenger. Would humans be on the menu? It's a question everyone wonders. The short answer, possibly. But humans would likely be a minor part of its diet. If a T-Rex were roaming and encountered an unprotected person, it might very well see a bipedal primate as prey. After all, we're meaty, soft, and slow. However, we're far smaller than a T-Rex's usual prey. A single human at 70 kilograms would be a snack, not a full meal for a 7,000-kilogram dinosaur. Bringing a predator as massive as Tyrannosaurus rex into our modern ecosystems would create a complex and potentially tense dynamic. Humans have spent thousands of years distancing themselves from nature's most dangerous animals. Suddenly reintroducing the ultimate apex predator would pose major challenges for both sides. For ecosystems, the arrival of a T-Rex would cause significant changes. It would immediately ascend to the top of the food chain, rearranging predator hierarchies wherever it lived. Lions or wolves would be forced to surrender kills to this towering newcomer, possibly changing their hunting patterns to avoid direct competition. Herd animals, too, would have to adapt. Species unfamiliar with such an immense hunter might become more wary, sticking together closely, or migrating differently to avoid known T-Rex territories. Yet there could be benefits. A top predator like T-Rex could balance ecosystems, controlling populations of large herbivores and indirectly benefiting plant life. It might even help maintain the overall health of prey populations by removing weak or sick individuals. However, the line between a balanced ecosystem and ecological chaos would be thin. Human response would be the ultimate factor in determining T-Rex's survival. Could we learn to share our world with a creature from deep time? Or would we end up repeating history, pushing yet another apex predator to extinction? North America today is home to bears, wolves, and pumas. Formidable predators, no doubt. But what if I told you there was once a cat that made all of them look small by comparison? Meet the extinct American lion, Panthera atrox. You know, the giant cat that could even make a grizzly bear go, "Nope, not today." This lion wasn't confined to one corner of the continent. Fossils have been found from Alaska to Mexico. Panthera atrox claimed territory in open grasslands, prairies, and light woodlands. However, it steered clear of dense forests where its smaller cousin, the jaguar, preferred to hunt. Instead, American lions patrolled Pleistocene plains alongside mammoths and bison. They vanished around 12 to 13,000 years ago, during the Great End Pleistocene extinction. Climate warming shrank their habitat and depleted their megafauna prey, and early humans were arriving on the scene as well. In other words, the last time American lions crossed paths with humans, it didn't end well for the lions. All of this raises an intriguing question. If the American lion were to make a comeback today, how would it adapt to survive in a world so different from the one it once ruled? If the American lion were to walk the forests and plains of North America today, it would certainly need a bit of a makeover. Forget the giant, cumbersome prehistoric cat image. We're talking about a leaner, sleeker, and smarter predator, optimized to survive modern challenges. First off, size matters, but bigger isn't always better. To slip quietly through dense forests and mountainous terrain without alarming every bird and hiker around, our modern American lion would have to scale down from its original weight of nearly 350 kilograms or 770 pounds. A more practical size today might be around 220 kilograms or 485 pounds, big enough to tackle prey, but small enough to maintain agility and stealth. To handle modern climates, the American lion might sport a versatile coat. Ice Age specimens likely had a short, tawny fur, with maybe a hint of a faint rosette or spot pattern for camouflage. They probably lacked the lush manes of African male lions. Cave paintings and mummified remains suggest Panthera atrox males were maneless or lightly maned. In a modern setting, if this lion ranged into cooler regions, it could grow a thicker winter undercoat like today's Siberian tigers or mountain lions, shedding it when seasons warm. Conversely, in hot deserts, a sleek coat would keep it cool. Its sandy, dun coloration would still provide cover in dry grass or forest shadows, just as it did millennia ago. Physically armed to the teeth, literally, The American lion's weaponry and senses would be key to its survival. It had large carnassial teeth and formidable jaws. One study estimates a big male's bite force at over 2,800 newtons, enough to crack bone if needed. Its canine fangs, about 8 centimeters long, delivered deep wounds, as one unlucky Ice Age bison discovered. Retractable claws up to 4 centimeters would grip prey and provide traction on today's terrain, from muddy riverbanks to rocky hills. With night vision 6 times better than a human's, an American lion could easily patrol at dusk or dawn, avoiding human eyes while scanning for deer silhouettes in the gloom. Its hearing would catch the slightest rustle of an elk in the brush, and it could likely detect the scent of a carcass from miles away. Lastly, it would retain one hallmark of true lions: a thunderous roar. If Panthera atrox roared, the sound might carry for 5 miles across the plains. A spine-tingling proclamation that the king of North America is on the prowl. Where could such a predator live today? The American lion would seek out wide-open spaces and abundant prey, much as it did in the Pleistocene. Its ideal habitat would be open grasslands, savannas, and sparse woodlands, environments where its size could be useful to full effect. In modern times, a region like the Yellowstone ecosystem or the plains of Montana and Wyoming might offer the elbow room and menu this big cat needs. There, herds of elk, bison, and deer still roam, and the cover of shrubs and rolling hills could let a lion sneak within striking distance. In cooler northern areas, Panthera atrox might venture into the fringes of boreal forests or tundra edges, places similar to where wolves and moose live. It likely wouldn't penetrate deep, dense forests. Those remain the realm of stealthier predators like cougars and bobcats. But mosaic landscapes would suit it well. Imagine this lion in the Canadian Rockies or Alaskan interior, padding through aspen parkland and alpine valleys, using rocky outcrops or shallow caves for shelter on winter nights. In contrast, the American Southwest's deserts could support a lion only where prey cluster around water. You might find one prowling the Sonoran twilight near a waterhole, where mule deer and pronghorn come to drink. Generally, a region with large herbivores and low human density could become this lion's kingdom. Large national parks and remote reserves would be prime real estate. It would avoid heavily populated coasts and Midwestern farm belts, steering clear of human-dominated landscapes. In short, Panthera atrox would thrive in the last wild corners of North America. From the high plains to the mountains, wherever the land is open, the prey is plentiful, and a giant cat can still be king. The American lion earned its throne by eating like a king. In the Ice Age, it feasted on the biggest prey around: deer, horses, camels, bison, even young mammoths. In a modern menu, mammoths and camels are off the table, but there's still plenty to chew on. A Panthera atrox today would likely target deer as its most frequent prey. White-tailed deer in the east, mule deer, and blacktails in the west. These animals are abundant and about the right size for a solo lion to take down. But this cat wouldn't stop at Bambi. Elk and moose would be high-value targets. A moose is dangerous to attack, but a desperate or experienced lion could succeed by ambushing one in thick brush or snow. Bison, the closest living ancestor to the lion's ancient favorite meal, still roam in pockets of the plains. An American lion would relish the challenge of a bison hunt. We know that they did in the past. In modern herds, a lion or two might single out juveniles or weaker adults, using strength and strategy to avoid those deadly horns and hooves. When hunting, this predator would probably employ a mix of stealth and power. Like modern big cats, it could stalk within a few dozen meters of prey, using whatever cover is available, then launch a lightning ambush. Its long legs and muscular build suggest it was a good sprinter. Fossil evidence even hints that pronghorn antelope, the fastest land animal in the Americas, ended up on the American lion's dinner list. Some scientists think Panthera atrox might have occasionally scavenged or pirated kills from smaller predators too. For instance, stealing a pronghorn carcass from the American cheetah, which roamed the same plains. If opportunity knocks, A hungry lion answers. Would the American lion live alone or in a pride? The honest answer is we're not entirely sure. Even scientists debate this. Modern African lions are famously social, living in prides, whereas most big cats are solitary. The American lion's own ancestor, the Eurasian cave lion, may have been solitary, hinting that Panthera atrox could have prowled alone. In a modern North American scenario, social structure might depend on the environment. In prey-rich open landscapes, a loose pride or family group might be advantageous. We might find a dominant male patrolling a territory that encompasses 2 or 3 females who cooperate to hunt. Meanwhile, in harsher or low prey regions, solitude could be the norm. In the modern world, the American lion's toughest competition wouldn't be another animal. It would be us, humans. Big cats and humans have a long, uneasy history, and Panthera atrox would be no exception. It would likely go out of its way to avoid people, much as mountain lions do today. These lions learned 13,000 years ago that humans can be dangerous and perhaps tasty on rare tragic occasions. So natural selection would make any survivors exceedingly wary of Homo sapiens. North America's existing carnivores would suddenly find themselves beneath a new apex. The gray wolf, for example, might recall its ancient fear of lions. A pack of wolves can harass and even injure a lone big cat, but Panthera atrox would be a formidable foe. In modern ecosystems, an American lion would likely dominate any carcass or kill site. If a pack of wolves brought down an elk, a hungry lion could roar and charge in. The wolves, smart creatures that they are, would probably yield their prize rather than risk those deadly claws. Over time, wolf packs might avoid areas a lion frequents, much like how coyotes give way to wolves, or how tigers keep wolf numbers low in parts of Asia. Coyotes, opportunistic but much smaller, would definitely steer clear, though they might trail at a distance, hoping to snack on leftovers once the lion moves on. Grizzly and black bears present an interesting rivalry. If a grizzly encountered an American lion at a kill, the outcome could go either way. The bear's sheer strength and aggression might intimidate the lion into retreat, much as solitary tigers in Siberia sometimes cede kills to large brown bears. On the other hand, if the lion is exceptionally large, or if it's a face-off between a lion pair and a single bear, the cat might successfully defend the carcass. Both are at the top of the food chain, so actual fights would be rare. More often, there'd be a standoff with a lot of bluffing. Perhaps each would size up the other and decide the meal isn't worth the injury risk. Mountain lions are much smaller and would be instantly overshadowed by Panthera atrox. In regions where the two coexisted, cougars would likely adjust their habits to avoid the big newcomer, perhaps shifting to heavier cover, hunting smaller game, and mainly active in times or places the lion isn't. We might see cougars retreat to steeper mountains and deeper forests that the bigger lion finds less efficient to hunt in. Jaguars, which barely range into the southwest today, could similarly be pushed back into dense jungles in Mexico and Central America, ceding open habitats to American lion. Humans might actually see an indirect benefit. With a top predator around, mid-sized carnivores like coyotes, bobcats, and even feral hogs could be kept in check, potentially leading to fewer of those predators around farms. It's the classic trophic cascade concept. Restoring an apex predator can rebalance an ecosystem, though it comes with risks and adjustments, of course. The Spinosaurus was a dinosaur that roamed the Earth almost 100 million years ago. It was a fearsome-looking beast and thought to be the longest-known carnivore the world has ever seen. It weighed up to 8 tons and grew up to 14 meters, or 46 feet long. Its sharp teeth filled its narrow, crocodile-like head, and along its back was a long sail or spine. Bony protrusions from its spine pointed upwards, more than 1.6 meters or 5 feet long. These were thought to be joined together by skin, creating a sail that ran the length of its back, although some scientists believe it was covered in a layer of fat, much like that of a camel's hump, rather than skin. Spinosaurus likely walked on its hind legs with two shorter front legs, in a similar stance to the well-known T-Rex. However, it may have also walked on all fours on occasion. Its body ended in a long tail which had a flattened, paddle-like structure, thought to help propel the dinosaur through the water. Scientists believe that this dinosaur was semi-aquatic, with the ability to dive below the water's surface to catch its prey. The Spinosaurus became extinct around 90 million years ago. But if it was resurrected, could it survive today? A lot has changed over the past 100 million years or so, and the world which Spinosaurus lived in was very different from today. Even so, if we look at the dinosaur's diet, habitat, and the environment it was used to, then we can determine whether it would survive nowadays. Firstly, diet. Scientists believe that Spinosaurus fed primarily on fish. Partially digested fish scales have been found in the stomach region of fossilized remains of Spinosaurus. There has been debate as to the use of Spinosaurus's large dorsal sail, but some speculate that it may have been used in capturing its prey. In a similar way to today's sailfish, Spinosaurus may have used its sail to herd schools of fish into a tight ball before capturing them in their jaws. It may have used its tail to thrash at the fish, temporarily stunning them, much as thresher sharks do. The sail would have acted like a centerboard to counteract the sideways motion of the tail as it thrashed about. The Spinosaurus was a generalist and opportunistic predator. Although it largely ate fish, it also predated on other small and medium-sized animals. A Spinosaurus tooth was found embedded in a pterosaurus's bone, suggesting that they may have eaten these flying reptiles as well. Its semi-aquatic lifestyle lent itself to hunting in freshwater, swamps, and possibly even coastal regions. The size and shape of the snout meant that it may have extensive sensory capabilities, allowing it to detect movement within the water, perhaps whilst its body remained submerged and concealed. Some studies have found their bones to be dense, which would help them to swim underwater in pursuit of prey. But some believe that Spinosaurus was much more of a land hunter, only hunting in the shadows or on the water's surface. Its lung placement likely meant that it could not dive or submerge itself like the crocodiles. These two contrasting views are widely debated. However, whether it was more of a land hunter or a water hunter, the semi-aquatic Spinosaurus had lightning-fast jaw speed, capable of snapping its jaws shut around its prey rather than slowly crushing it. If it was alive today, it would probably occupy a similar niche to today's crocodiles and alligators. It may even compete with them for space, territory, and food. Just as crocodiles eat fish, small mammals, and reptiles, such as turtles, Spinosaurus would do the same. Aquatic life during the Cretaceous period was thriving. In the oceans, Mosasaurus, plesiosaurs, and modern-day sharks appeared. Less is known about the freshwater habitats, but fish were likely to have been abundant. No one knows how much Spinosaurus ate, but with such a huge body size, it may have needed to hunt large prey, and often. Crocodiles can go months without feeding, but when they eat, they can consume as much as half their body weight in one sitting. It's probable that Spinosaurus preyed upon huge freshwater fish found in its river ecosystems. However, there may not be enough food for a population of Spinosaurus to thrive in today's world. Overfishing and pollution of our waterways are decimating fish populations and have a knock-on effect throughout the food chain. Furthermore, more than half of today's crocodilians are under threat of extinction due to loss of habitat, hunting, bycatch and fishing gear, and damming of rivers. So, food may not be available for Spinosaurus to thrive today. But what about other aspects of life? Let's consider the Spinosaurus's habitat and the climate in which it lived. Understanding this could help us determine whether it could survive on Earth today. Most fossilized evidence of Spinosaurus comes from what is now northern Africa, mostly Egypt and Morocco. It lived on tidal flats, amongst mangrove swamps, and alongside inland lakes and rivers. The temperature of the Earth was a lot hotter during the late Cretaceous than it is today. During the hottest times of the year, rivers and lakes would have dried up. Spinosaurus would have changed its hunting strategy to take down land-based prey during these times. By the end of the Cretaceous period, most of today's continents had split away and were in a similar position that they're in today. There were high rates of seafloor spreading, which resulted in a large amount of volcanism.
This created a warmer and more humid environment than today, with very few ice sheets and glaciers at the poles, except on high mountains. The formation of mid-oceanic ridges caused the sea levels to rise by as much as 250 meters higher than they are today. Temperate conditions extended to the poles, and much of the north was under a tropical and subtropical climate. There would likely be some suitable waterways around today for Spinosaurus to inhabit. They may compete with crocodiles in North Africa for territory, though. The Nile crocodile is the largest in Africa and is found in the Nile throughout Egypt. But it would be no match for the enormous Spinosaurus. Fish stocks would take a hit if a large predator was introduced to the ecosystem. There has been speculation about the Spinosaurus's fin-shaped dorsal spine. As previously mentioned, it may have been used in hunting within the water, but it also could have been used as an elaborate display for mating rites. Others have suggested that it could have been used to help with thermoregulation. By increasing the surface area, it would have allowed more heat to dissipate, cooling the animal down. Or it could have been used to absorb more heat in cooler temperatures. If it was used to regulate the body temperature, then it could be assumed that the dinosaur could survive in a range of temperatures. However, we don't believe the climate would be suitable. The late Cretaceous was considerably warmer than it is today. There was little difference between annual seasons, and the environment was much more humid. There was more carbon dioxide in the atmosphere, as it was released from weathered carboniferous rock, creating a greenhouse effect. Fossils have revealed wide tree rings near northern latitudes and a high density of tree cover. Alaska had vast swamps, and winter temperatures in Siberia's Arctic Circle got as low as 6 degrees Celsius, compared to -37 today. Where there are currently barren snowfields and tundra in Siberia, there was plant life for much of the year throughout the Cretaceous. All this evidence suggests that the conditions near the poles were warmer and wetter. Nearer to the equator, conifers were suggesting the equator was drier. These conditions are opposite from today. Placental mammals evolved during the late Cretaceous, ready to take over the planet after the dinosaurs' imminent extinction. But Spinosaurus became extinct before the mass extinction of the dinosaurs. In fact, about 30 million years before T-Rex existed. It is believed that Spinosaurus died out due to extreme drought because they were so reliant on water and swamps for their survival. With such a difference in climate, and possibly not enough food to eat, we don't believe Spinosaurus could survive nowadays. The Earth's climate has been through so many cycles and variations over the millennia that animals have adapted to the era in which they evolved. Only some species, like some crocodilians and some sharks, have miraculously survived relatively unchanged for tens of millions of years, which is a remarkable feat for any animal. Homotherium was a genus of scimitar-toothed cats. Although they were similar in appearance to Smilodon, Homotherium's canines were shorter and likely covered by the lips, and their body was more conducive to chasing prey rather than ambushing it. In size, they could be comparable to today's male African lions. They weighed around 190 kilograms, or 420 pounds, and stood at 1.1 meters, or 3 feet 7 inches at the shoulder. Homotherium was widespread across the globe, inhabiting both North and South America, as well as Eurasia and Africa, between 4 million and 12,000 years ago. Their presence on each of these continents varied through the Pliocene and Pleistocene, first becoming extinct in Africa 1.5 million years ago, Eurasia 30,000 years ago, and North America 12,000 years ago. It is thought to have had the largest geographical range of all saber-toothed cats. However, it is not clear whether they occupied these locations simultaneously. Although they are often compared to Smilodon, the lineage that was to become Homotherium diverged from that of Smilodon around 18 million years ago. Could these large cats survive nowadays? Would there be enough prey? Would there be suitable habitat? And could they survive today's climate? Homotherium had physical characteristics, which suggested that it hunted in open environments, chasing its prey over significant distances. It had reduced claws, more slender limbs than the ambush predator Smilodon, and a sloping back. They were unlikely to be as fast as today's cheetahs, which sprint over short distances, but they were more likely to run over longer distances. As well as the sloping back, Homotherium had powerful hind legs and a powerful lumbar region, which made it capable of pulling down significant loads. In fact, it seems from fossil evidence that homotherium attacked and killed youngsters of the elephantid Dinotherium on the African continent and baby mammoths in North America. As well as being similar in size to modern-day lions, homotherium was also a social hunter like lions. This behavioral adaptation would have enabled them to take down large prey, including juvenile mammoths. Their elongated canines would have made securing such large herbivores easier than it is for today's lions, as they would have been able to slice through thick hide. From the shape and structure of their skull, scientists believe that homotherium had an incredibly powerful bite force that enabled it to bite down on its victims and hold on. Unlike with Smilodon, however, there are fewer fossils of broken canines from homotherium. This suggests that the large cats hunted as a group, completely immobilizing their prey before delivering the fatal bite with their characteristic canines. From fossilized mammoth remains, scientists have concluded that homotherium often dismembered its kill and then dragged the parts of the carcass back to the caves, where it could be well guarded from the likes of dire wolves and American lions, and eaten at leisure. Judging by the wear and tear of the teeth, homotherium did not consume bone like other large carnivores of the time, only the flesh of the animal. Genetic analysis of homotherium fossils has found links with genes that are linked to diurnal behavior and a cursorial lifestyle. Although homotherium appeared to have excellent eyesight and good night vision, it is thought that they hunted during daylight hours and were adapted to running. From studying the carbon-stable isotopes and microwear on fossilized homotherium teeth, scientists have been able to determine that these large cats preferred prey from open habitats. They could tell from the data that homotherium's prey grazed grasses rather than vegetation found in forested habitats. In one of the cat's dens, fossilized remains of baby mammoths, approximately 2 years old, were the most common prey species. But it is also thought that they fed on bison and horses that grazed the open grasslands of North America. If homotherium was to survive today, its most likely prey would be bison in North America and Eurasia, and young elephants in Africa. It seems that they targeted larger animals so, although there may be an abundance of prey species like deer and antelope across the continents, homotherium almost certainly wouldn't hunt these. And considering bison are protected in both America and Europe, they wouldn't be suitable prey for these cats. In Africa, there are some areas where elephants are culled due to the damage their large numbers cause to habitats and surrounding farmland. But in other areas, they are fiercely protected. Maybe homotherium could hunt elephants where officials are trying to keep their numbers down, but it would be a precarious existence. Other predators may now compete with homotherium on the African plains. But if they did hunt there, could homotherium survive the climate nowadays? And if they hunted elephants in Africa, is the habitat suitable for them? During the lifetime of the homotherium genus, they endured a vast range of temperatures. This change in climatic conditions was gradual, unlike climate change happening today. This allowed species to adapt and change, or move and relocate. Overall, the Pliocene was a transition from the warm Miocene period to the cold Pleistocene epoch. The conditions during the Pliocene resulted in more seasonal climates and colder and drier regions across the globe. Midway through the Pliocene, however, there was a significant rise in global temperatures, 2 to 3 degrees Celsius warmer than they are today. As temperatures cooled once more towards the end of the Pliocene, the vegetation and flora changed. Whilst deciduous trees proliferated and coniferous forests covered much of the north, tropical forests became limited to a narrow band around the equator, and many tropical species died out. Woodlands and forests gave way to open grasslands and savannas, and deserts appeared in Africa and Asia. The changing climate had a significant impact on the flora and fauna. Habitats changed, and species had to adapt or die out. Following the Pliocene, the Pleistocene was signified by much colder temperatures. As much as 30% of Earth's landmass was covered by glaciers and ice sheets extending to mid-latitudes. Temperatures were between 12 to 20 degrees Celsius, or 53 to 68 degrees Fahrenheit colder near the ice sheets than they are today. The homotherium genus survived this huge range in climate. And not only that, but it is thought that they lived in a range of habitats too. Although evidence suggests that homotherium predominantly resided in open habitats where its prey was abundant, There is also evidence of some species living in dense vegetation. Its ability to thrive in a range of habitats and under a variety of climatic conditions makes this genus of big cat exceptionally hardy and suggests that it could survive in parts of the world today. Homotherium appears to have been a genetically diverse genus of big cats. Individuals from different populations likely traveled great distances, increasing gene flow throughout the global population. It occupied a broad geographical range and likely inhabited a few different habitats. Its behavior made it unique amongst other large cats of its day, such as its diurnal and social hunting techniques. This allowed it to occupy its niche without the need for competition with other predators during the Pliocene and Pleistocene epochs. Although Homotherium was a hugely successful prehistoric predator, it didn't make it to the present day. This may be surprising considering the unique adaptations it had, which gave it so many advantages. But these adaptations that once made the genus highly successful may have ultimately led to its downfall. They were highly adapted to capturing large prey, and as the large herbivores died out following the Quaternary extinction event, Homotherium was unable to adapt its hunting techniques to take advantage of the smaller prey species remaining. It is because of this that we believe Homotherium would not be able to survive today. They could likely survive today's climate, although the rate at which climate change is happening far exceeds anything the big cats have experienced in the past, so this could be challenging. They would also likely find enough habitat in some of the wilderness that remains today, but without large prey available for them to hunt, they wouldn't be able to successfully feed. Without the ability to switch their hunting strategies to take down smaller prey, we believe that they couldn't survive nowadays.
Quetzalcoatlus was a genus of large pterosaur, or flying reptiles. They lived during the late Cretaceous period and consisted of two known species, Quetzalcoatlus northropi and Quetzalcoatlus lawsone. Their wingspan has been estimated between 10 and 11 meters, or 33 to 36 feet, and standing on their back two legs, their shoulders would have reached heights of 3 meters, almost 10 feet. They have a reputation for being the largest flying animal ever to have lived. But could they survive nowadays? Having a giant flying reptile soaring in our skies certainly wouldn't go unnoticed in our modern world. Quetzalcoatlus was most common in what is now known as Texas. There have been a large number of fossils found there, but there is still debate about the lifestyle of these gigantic creatures. Some scientists have predicted that the pterosaurs were scavengers, mostly feeding like today's marabou storks. Any carcasses that littered the open plains would have been available for the Quetzalcoatlus to take advantage of. However, a more recent analysis of Quetzalcoatlus's feeding behavior suggests that their beak wasn't built for ripping meat from a dead animal in the same way that vultures are. It lacked the essential hook at the end of it, and the beak didn't seem to close completely either. Instead, it was suggested by some that these flying reptiles skimmed the surface of the oceans, catching fish in their enormous beaks. But again, this idea was dismissed due to the energy efficiency for their size. They would have created too much drag. Not only that, but their fossils have only been found hundreds of miles from the nearest coastline, and with no evidence of fresh waterways nearby. Now, the general consensus is that Quetzalcoatlus hunted small vertebrates on the open plains. They were adapted at walking on all fours, using their forelimbs just like a four-legged mammal does today. It was unusual in that its wings folded to create its forelimbs, which were the same length as its back legs. This made it efficient at walking, and less cumbersome than some of the smaller pterosaurs. Furthermore, they could turn their heads 180 degrees, which helped them to keep an eye out for predators whilst stalking their own prey. Today, the open plains of North America would provide a similar habitat for Quetzalcoatlus. Although mammals were small during the Cretaceous, and the flying reptiles would likely have fed upon terrestrial reptiles, today, the Quetzalcoatlus would have more prey choice. They could pluck the likes of marmots, hares, rabbits, and chipmunks from the long grass. Ground-nesting birds could also be considered prey, as well as some reptiles that the Quetzalcoatlus would be used to feeding on. Their feeding behavior has been likened, by some, to that of egrets and herons. If the Quetzalcoatlus found inland water, then it may slowly stalk through swamps and still fresh water and grab unsuspecting fish from just below the surface. Today, the largest flying birds in the world include the wandering albatross, the Andean vulture, and the cinereous vulture. but even they would be dwarfed by the quetzalcoatlus. If the quetzalcoatlus took to the skies, it would dominate the skyscape. However, it would unlikely compete with these others for food. Wandering albatrosses fish the open oceans for their prey, whilst the Andean and cinereous vultures are primarily carrion feeders. Despite their impressive flying capabilities, with some scientists predicting they were able to reach speeds of 80 miles per hour and fly non-stop for more than a week, they needed to land to find their food. Although it is now believed that the giant quetzalcoatlus didn't skim the oceans hunting for fish, some pterosaurs did and were snatched out of the sky by large predatory fish and sharks. On the ground, quetzalcoatlus was likely targeted by some of the carnivorous dinosaurs of the late Cretaceous. In North America, these were mostly the famous T-Rex and less well-known gorgosaurs. Further north in Canada, a formidable predator was Albertosaurus. And to the south of Argentina were the predatory Gigantosaurus and Carnotaurus, which likely would not have crossed paths with Quetzalcoatlus. Today, having size on their side would make the Quetzalcoatlus difficult to target for many predators. Of the larger predators that live in North America nowadays, brown and black bears are the most likely to be able to take down a Quetzalcoatlus. Smaller mountain lions, wolves, and coyotes probably wouldn't be large enough to cope with a full-grown Quetzalcoatlus. However, hunting in packs could make them a formidable presence. If the flying reptiles walked through North America's swamps, then they could also be the target of alligators and American crocodiles. Although Quetzalcoatlus are considered predators, they would likely have less of an impact on the ecosystem today than introducing other prehistoric reptiles. They would be less likely to compete for the top spot amongst North America's apex predators. It is not known whether they were territorial, but they probably wouldn't fight off any bears that came close to their hunting grounds, as they were not adapted to fight in the same way that some of the carnivorous dinosaurs were. Feeding on small vertebrates, like rodents and rabbits, may impact other species like foxes and coyotes that rely on them as a large part of their diet. However, these smaller prey species are typically numerous and tend to bounce back from shortfalls in their populations. If Quetzalcoatlus turned to preying on fish, then they could pose a problem for North American bears. Seeing both grizzlies and Quetzalcoatlus peering over the edge of a waterfall during the salmon run could be quite a sight. If food was abundant, such as when salmon come to the rivers to spawn, bears would be less likely to chase away Quetzalcoatlus. However, if prey was scarce, then there is more likely to be interspecies conflict. Although the smaller pterosaurs were thought to live in flocks like some wading birds, it is believed that the Quetzalcoatlus was primarily solitary. Therefore, it would pose less of a threat to the likes of bears if a particular food source was being fought over. The Quetzalcoatlus's habitat was thought to be open plains. They would have struggled to take off in heavily forested areas. By the late Cretaceous, flowering plants had emerged and grasses were growing across North America. Before this, the landscape was dominated by fir trees and ginkgos. Today, there are plenty of grasslands across North America, with the Great Plains covering around 500,000 square miles. This would provide the food, in the form of small vertebrates, that Quetzalcoatlus would feed on. It was believed that Quetzalcoatlus didn't run along the ground to take off. Its enormous wings would have got in the way of that. Instead, it seemed that they used their powerful and muscular back legs to leap into the air. They then flapped their wings to climb into the sky. They had immensely powerful chest muscles and flexible wings, which gave them stability during turbulence and allowed them to soar at great heights and over great distances. Today, they could cover a wide area relatively quickly, meaning that they could be widespread across North America if they could find means to survive. Although they would be an impressive sight, the size of Quetzalcoatlus may not be favorable in today's modern world. Could the enormous size of Quetzalcoatlus be its downfall? During the late Cretaceous period, the Earth saw one of the largest animals ever to have existed. This was when the largest sauropods, called the Titanosaurs, roamed the Earth. It is not fully understood why the dinosaurs as well as the likes of the Quetzalcoatlus were so enormous during this time. Some believe that it was because of the gases in the Earth's atmosphere. Others believe that it was an evolutionary arms race between predators and prey. If Quetzalcoatlus lived today, where animals are nowhere near as large as they were 66 million years ago, they may change over time to adapt to the modern ecosystem. Not only is the atmosphere different with different compositions of gases, but there aren't so many large predators to compete with. as we saw with more recent extinction events, like the extinction of the megafauna from North and South America. 10 to 50,000 years ago, animals have turned towards being smaller in size. Being so large means that an individual requires more energy and food to survive. Finding enough prey today in a world that is dominated by humans with ever-shrinking natural habitats could mean that there is less for quetzalcoatlus to eat. Also, with relatively few predators considered big enough and bold enough to prey on quetzalcoatlus, they may not need to be so enormous.
Smilodons, or more commonly known as the saber-toothed tiger. Powerful and ferocious. These prehistoric cats once populated North and South America. They were carnivorous predators, hunting large prey such as the woolly mammoth and bison. There were 3 species of Smilodon that lived from 2.5 million years ago until 10,000 years ago. Smilodon gracilis and Smilodon popilator were found in South America, and Smilodon fatalis was found in North America. They all belong to an extinct subfamily of Felidae. Their characteristic feature was the elongated canine teeth, giving them the well-known name of the saber-toothed cats. The 3 different species of Smilodon differed significantly in size from one another. The smallest, Smilodon gracilis, was comparable to modern-day jaguars, and Smilodon fatalis was similar to Siberian tigers. Smilodon popilator, however, was the largest of all, weighing in at 220 to 360 kilograms. Some fossils of this species have even found them to have weighed up to 400 kilograms. Scientists have been able to study large numbers of Smilodon fossils found in the Los Angeles tar pits at Ranchero La Brea. They've been able to determine that the Smilodon's most likely behavior from skeletal morphology and animal paleopathologies showing the animal's stresses, strains, and injuries. Some scientists suggest that the saber-toothed cat was a social species, similar to that of modern-day lions. This belief has risen from fossils that have been found to have injuries that have healed long before the animal has died. It is assumed that an animal would need assistance to survive an injury in the wild. This suggests Smilodons work together, like a pride of lions. The counter-argument to this is that modern-day cats heal quickly without needing help. For example, to eat. Furthermore, Smilodon's relatively small brain is not in keeping with that of a social species. Saber-toothed cats are known to have been ferocious predators. You would have been forgiven for thinking that they were similar to today's big cats. However, their approach to hunting differed slightly. Smilodon had very powerful front limbs, suggesting that these were key to catching prey. Their long, elongated canines were prone to breaking, and so the big cats relied more heavily on immobilizing their prey with their front limbs before biting to kill. They would use their front legs to knock their prey to the ground, or cling on and pin them down. Today's big cats often hold onto their prey with their teeth during an attack. It was once thought that Smilodon hunted in open grassland, taking down large herbivores such as bison. This myth has now been debunked, and more recent research suggests that Smilodon actually hunted in forests and amongst the shrubbery rather than chasing prey in the open. Smilodon was more of an ambush predator, using the forest to remain hidden. They fed on large species such as giant ground sloths and the macrauchenia, which looked a bit like a large llama. Hunting in the forest meant that the saber-toothed cats probably didn't compete with grassland hunting carnivores, such as the dire wolves. Smilodons were around during the Pleistocene, but became extinct by the Pleistocene-Holocene boundary. The climate during the Pleistocene varied and changed enormously. Within a few decades, temperatures fluctuated by as much as 10 degrees Celsius, and there were irregular cycles of glacial and interglacial cold and warm periods. So why did the Smilodon go extinct? Did the rapidly changing environmental conditions lead to their demise? Or did early humans play a role? People believe that overkilling the Smilodon was responsible for its demise. This is because their extinction coincided with the arrival of the first humans to North America. However, this may not be the case. 38 genera became extinct in North America by the end of the Pleistocene, Little to no fossil records show death from human attack on the larger mammals, but there has been plenty of fossil evidence showing humans hunted bison and elk. Bison and elk still survive to this day, so clearly overkill from humans was not to blame. Furthermore, it seems there was limited genetic diversity towards the end of the Pleistocene, caused by the changing climate and shifts in the animals' ranges. Some scientists are looking at the environmental fluctuations that occurred during the Pleistocene to predict outcomes for changes in our current global climate. The pressures faced by the Smilodon and other coexisting species were numerous and complex. The mass extinction towards the end of the Pleistocene included a huge range of animals. Not all large mammals became extinct, and some smaller species and trees disappeared too. Some inhabited warmer climates, others endured the cold. Some were herbivores, some omnivores, and some, like the Smilodon, carnivores. Some were social animals, and some were solitary. It is thought that each and every species during the climatic changes of the Pleistocene had to adapt, migrate, or become extinct. It appears some species were better at adapting than others. It seems the Smilodon was not one of them. The smaller predatory species of the Pleistocene, such as the coyotes and wolves, have survived to the modern day, whilst the larger predators, including Smilodon, became extinct 10 to 12,000 years ago. Their extinction could have been, at least partly, attributed to the hotter and more humid climate at the beginning of the Holocene. Their inability to adapt to these changing temperatures could be responsible for their extinction. It is also probable that the specialized diet of the Smilodon contributed to their fate. Species like the coyote adapted to changes by hunting smaller prey and becoming more of a scavenger. Both the dire wolves and the saber-toothed cats showed no sign of changing their dietary preferences in response to the evolving ecology. Smilodon's extinction followed the mass extinction of the prehistoric herbivores, including the mammoths, giant sloths, and mastodons. The smaller predatory species survived by adapting their hunting behavior and becoming physically smaller. Today's coyotes are significantly smaller than their predecessors. The size of a Smilodon did not change throughout the Pleistocene. So, the question here today is, could Smilodon survive nowadays? For such a fearsome and ferocious beast, the Smilodon didn't appear to be very adaptable to climate changes. The current environmental conditions of the Earth are similar to those during the interglacial periods in the Pleistocene. This suggests that, from an environmental and climatic point of view, Smilodon could survive today. Finding prey, however, could be difficult. The exceptionally large species that Smilodon once hunted, such as the woolly mammoth, no longer roam the Earth. Smaller animals, like bison and elk, however, can still be found on the North American plains, albeit in much smaller numbers. These were common prey for the saber-toothed cats, but the only wild bison now found in North America are within national parks. Yellowstone National Park is the only place to have truly wild bison, thought to be descended from those of the Pleistocene era. In South America, alpacas, llamas, peccaries, capybara, and deer could be considered prey species for the Smilodon. Jaguars currently hunt some of these species, and whilst jaguars didn't compete with Smilodon during the Pleistocene, in today's world they may do. With smaller habitat ranges available and smaller prey animals, apex predators are likely to be forced to compete with each other. The predatory animals currently living in North and South America are surviving and occupying the niche that was once filled by the Smilodon. If saber-toothed cats were able to be reincarnated and reintroduced into the wild, it is unlikely they would survive. The species we have nowadays are more adaptable. When human interference is limited, bears thrive partly due to their broad dietary range. As well as eating meat, they eat berries, insects, and leaves. Wolves are social predators, unlike Smilodon, hunting in packs to take down larger animals. Both of these predators would compete with Smilodon for prey and territory. In South America, the jaguar has decreased in size since the Pleistocene. It has adapted very well to the damp habitat of the rainforest. It prefers to hunt smaller animals, such as rodents and monkeys, and can hold its breath underwater for up to 5 minutes whilst catching fish. It is difficult to imagine that Smilodon, once a successful apex predator, could survive today. Massive loss of habitat, reduction in the numbers of wild prey, and the presence of successful, more adaptable apex predators suggest Smilodon would struggle to survive.
Allosaurus was a large theropod dinosaur that roamed the Earth 155 to 145 million years ago during the late Jurassic period. Like most theropods, Allosaurus walked on 2 powerful hind legs and had shortened forelimbs like the well-known T-Rex. Some specimens have been found to be as much as 9.7 meters, or 32 feet long. They were ferocious carnivores with large heads and jaws full of sharp teeth. Although some believe that a real-life Jurassic Park would be an incredible sight, here we ask the question, could Allosaurus survive nowadays? Firstly, let's consider diet. Owing to their enormous size, scientists believe that Allosaurus hunted large prey. There has been solid evidence of this from the fossilized remains of both allosaurs and herbivorous prey species. One injury that has been preserved through time was a puncture wound found on the Allosaurus, made by the tail spike of a Stegosaurus. Defending themselves against these predators was common, and another Stegosaurus skeleton showed a U-shaped chunk taken out of its neck, which fitted the size and shape of an Allosaurus snout. It seems the Allosaurus considered the highly armored Stegosaurus as common prey. There is debate about exactly how Allosaurus hunted. They are known to have eaten sauropods, which include the largest terrestrial animals ever to have walked the Earth. Diplodocus and Brachiosaurus belonged to this group, which had characteristically long necks, allowing them to eat from the very tops of trees. Although Allosaurus was an enormous predator, it was still dwarfed by some of these sauropods. Therefore, to hunt a full-grown adult may have required pack-hunting behavior. Their jaws were thought to possess stretchy ligaments, enabling them to open their mouths at a 92-degree angle. They could have closed them around the necks of their prey, similarly crushing the trachea of some of today's big cats. However, their teeth were small, unlike other theropods, suggesting they used them more like a saw, rather than crushing through muscle and bone. The sharp teeth would have delivered significant injuries, which the prey animal later succumbed to, similar to today's Komodo dragons. This would mean that allosaurs wouldn't need to latch onto a large animal like Diplodocus to bring it down. Instead, their bites would inflict wounds that would weaken the animal, and they could track it until it eventually died. Also, their jaws weren't as powerful as the mighty T-Rex, but they had considerably more control over their heads and mouths due to their strong neck muscles. They would have eaten carrion too, but rather than shaking their heads from side to side like T-Rex and modern-day crocodiles to rip meat from a carcass, they would have pulled the flesh upwards like falcons. Their forelimbs seemed to be more useful than those of other theropods. They could use them to hold down the dead animal, whilst they ripped the meat off the bone with their jaws. But what would Allosaurus eat in today's modern world? The largest land animal alive today is the African bush elephant. It stands at 4 or 5 meters tall and weighs up to 6 tons. In comparison, Stegosaurus measured 3 to 4 meters tall and weighed between 3 and 5 tons. They are comparable by size, and elephants would likely be far easier to target than the heavy armored Stegosaurus. Also on the list of the largest modern animals are rhinos, hippos, giraffes, bears, and gaur. Although these wouldn't match the likes of Stegosaurus, and certainly not Diplodocus or Brachiosaurus for size, they may provide some nourishment for allosaurs in today's world. Whether these would be enough, especially considering many of these animals have small population sizes and are under threat of extinction themselves, is another question. Did Allosaurus eat the entire carcass of a sauropod? Or did it just hunt the larger dinosaurs because they were less agile than the smaller species? It is estimated that the top speed of Allosaurus was between 19 and 34 miles per hour. The top speed of elephants is 25 miles per hour, and for rhinos it is 31 miles per hour. This is considerably faster than Stegosaurus, which had a top speed of 11 miles per hour. Maybe today's modern species would be too fast for Allosaurus.
If allosaurus did hunt in packs during the Jurassic, then they wouldn't necessarily need to in modern times, as they would dwarf any of today's creatures. But it may be a way of targeting faster animals, using collaborative hunting to approach the prey from different angles. There is still some debate regarding the social structure and potential group hunting behavior of allosaurus. Fossilized remains, particularly shed teeth found in carcasses, suggest that allosaurus killed its prey and then brought it back to its lair to feed its young. Some believe that they cared for their young until they were fully independent. Others lean towards a more solitary existence for the allosaurs. It is relatively rare for large vertebrates to hunt together. Although some will tolerate each other when it comes to scavenging a carcass, many interactions amongst carnivores of the same species are aggressive and territorial. Although modern prey would be easier for allosaurus to capture, we don't think it would be sufficient to sustain their appetite. But what about the habitat that allosaurus lived in? Most of the allosaurus fossils have been located in Western America and Portugal. The Morrison Formation is a layer of sedimentary rock that covers Western America from Montana to New Mexico. Contained within it are copious amounts of fossils, which provide insight into the plant and animal life during the Jurassic. The habitat in which allosaurus lived was semi-arid, with distinct wet and dry seasons. There was plant life in the form of conifers, ferns, mosses, and cycads. There were rivers lining these forests and flat open floodplains in which the allosaurus could hunt. Fellow theropods that shared this habitat with allosaurus included Ceratosaurus and Torvosaurus. These were physically shorter than allosaurus and more agile. They preferred hunting amongst the forests and underbrush, whilst allosaurus preferred the open plains. Today, there would likely be some habitat that the allosaurus would find suitable. There are open plains across most of the continents, which would allow the enormous predator to locate its prey. If introduced to these ecosystems, however, and if it somehow survived on the meager food sources available, it would probably decimate the species that live there. During the Jurassic period, allosaurus was at the top of the food chain, but would occasionally have been predated on by other large theropods. There is fossil evidence of allosaurs being eaten by other theropods, but it has been suggested that this was mostly through scavenging, rather than actively hunting the dinosaurs. Today, no other animal would challenge the allosaurus, and their presence could be devastating. Could they survive the climate in our modern world? Evidence shows that the Jurassic period was warmer than today by as much as 5 degrees Celsius to 10 degrees Celsius. There were no ice caps at the poles, and the temperate regions would have been more like subtropical and tropical climates. Regions closer to the equator were arid, whilst higher latitudes were wetter. Some of the land was covered in vast swamps and wetlands, creating a humid environment in which allosaurus thrived. The diversity of ferns, palms, and conifers suggest that the climate was warm and humid, and their spread towards the poles shows that there was less of a temperature difference between the polar regions and those near the equator. In contrast, today's temperatures are significantly cooler, and there is an obvious temperature gradient along the latitudes. The oceans were thought to be 8 degrees Celsius warmer than modern times, allowing corals to thrive 10 degrees latitude further north and south from where they are today. Although there may have been some snow following intermittent cold snaps in the climate, the summers were too warm to allow glaciers to form, except perhaps high up on the mountains. The atmospheric carbon dioxide was 4 times greater than it is today. This caused a greenhouse effect, which bathed the globe in a warmer climate. The animal life on Earth would have been adapted to survive and thrive in these levels of carbon dioxide. If allosaurus were introduced to today's world, then they may not survive the differences in atmospheric gases. In conclusion, we don't believe that allosaurus could survive nowadays. The world is a very different place from the Jurassic period. Not only has the climate changed dramatically, but we believe the allosaurus would struggle to find enough prey of a suitable size to survive.
When you think of the largest snake in the world, one name slithers into everyone's mind: the anaconda. These modern giants are masters of their environment, capable of taking down prey much larger than themselves. But what if I told you that, in the history of the Earth, the anaconda doesn't even come close to being the largest snake to ever exist?
Millions of years ago, the Earth was home to colossal serpents that dwarfed even the biggest anaconda alive today. They ruled rainforests, swamps, and even ancient oceans, striking fear into the hearts of creatures around them. These prehistoric snakes weren't just big, they were record-breaking predators. Long before the end of the age of dinosaurs, a colossal snake known as madsoia ruled the dry and unforgiving landscapes of what we now know as South America. This giant, measuring up to 10 meters or 33 feet in length, wasn't lurking in dense jungles or wetlands. Instead, it hunted in semi-arid environments where ambush predators had to rely on patience and power to secure a meal. Unlike modern constrictors that prefer tropical habitats, madsoia adapted to a harsher world. Fossils show it wasn't built for speed or rapid strikes. Instead, its large, heavy body was designed for crushing strength, ideal for subduing large reptiles, mammals, and even small dinosaurs that roamed these ancient landscapes. This slow but deadly approach made it a dominant predator in its ecosystem. The fossils of madsoia, particularly its vertebrae, reveal a creature adapted to life on land rather than in water. These bones were thick and strong, designed to support the weight of its muscular frame as it coiled and constricted prey. Compared to modern snakes, madsoia was less flexible, but it didn't need to be. Its sheer power was enough to overwhelm most creatures it encountered. As a part of the Madsoidae family, madsoia represents a fascinating group of prehistoric snakes that existed across Gondwana. Relatives of this species have been found in locations as far-flung as Madagascar and Australia, showing how widespread these snakes were before their extinction. 50 million years ago, the tropical seas of what is now northern Africa were home to a massive snake that dominated the waters, Paleophis colossus. Stretching up to 12 meters or 39 feet in length, this marine predator was unlike the land-dwelling snakes of its time. It moved through ancient estuaries and shallow coastal waters, preying on a variety of aquatic animals. Fossils of Paleophis colossus, including its enormous vertebrae, were discovered in Mali. These bones reveal a snake perfectly suited for life in the water. Its body was elongated and less flexible than terrestrial snakes, which helped it move efficiently through currents and maintain stability while swimming. Unlike modern sea snakes, it wasn't venomous. Instead, it relied on its size and strength to overpower prey, likely including large fish, aquatic reptiles, and possibly small marine mammals. This massive snake belonged to the Paleophis genus, a group of marine snakes that evolved to exploit the abundance of life in ancient seas. Paleophis colossus was one of the largest species in the group, standing out for its size and adaptability to thrive in habitats where land-based predators couldn't compete. It likely used ambush tactics, hiding among submerged vegetation or along the seafloor to strike unsuspecting prey. The habitat of Paleophis colossus wasn't limited to oceans. It also inhabited brackish estuaries and river mouths, where freshwater mixed with saltwater. These areas were rich in biodiversity, providing an ideal hunting ground. Its dual ability to navigate both coastal and inland waters may have given it an advantage over other marine predators. The cooling climate of the late Eocene, along with shifts in sea levels and marine ecosystems, likely marked the decline of Paleophis colossus. 40 million years ago, in what is now North Africa, Gigantophis garstini slithered through a vastly different landscape. The Sahara was not the endless desert we know today, but a land of rivers, wetlands, and lush vegetation teeming with life. At an estimated length of 10 meters or 33 feet, this enormous snake was one of the apex predators of the region, hunting in environments that supported a wide variety of large mammals and reptiles. Fossils of Gigantophis were first discovered in Egypt, revealing a snake built for brute strength. Its large, thick vertebrae suggest a muscular body capable of constricting prey with incredible force. Unlike aquatic snakes like anacondas, Gigantophis likely hunted on land, targeting sizable prey such as homotherium, a small hippo-like ancestor of elephants, and other large animals that ventured too close. The habitats of Gigantophis were rich in biodiversity, with networks of rivers and floodplains providing ample hunting opportunities. This snake's size and power placed it at the top of the food chain, with little competition from other predators.
Its ambush tactics, waiting in silence before striking with speed and precision, made it a formidable hunter, capable of tackling prey many times its own weight. The world of Gigantophis garstini was undergoing significant changes during its time. Shifting climates and the gradual drying of its lush habitats likely had a profound impact on its survival. The once fertile floodplains began to transform into the arid regions that would eventually become the Sahara Desert, taking with them much of the prey and conditions that allowed such a massive snake to thrive. The discovery of Gigantophis in the early 20th century captivated scientists who initially believed it to be the largest snake ever. Deep in the tropical rainforests of South America, around 60 million years ago, an unimaginable predator lurked in the shadows. At a staggering length of up to 13 meters or 43 feet and weighing over a ton, Titanoboa cerahonensis was the largest snake to ever exist. This prehistoric giant emerged in the Paleocene epoch, a time when the Earth was recovering from the mass extinction that wiped out the dinosaurs. In the absence of large terrestrial predators, Titanoboa rose to dominance, ruling the swamps and rivers with unmatched power. The discovery of Titanoboa fossils in the Cerrejón coal mines of Colombia sent shockwaves through the scientific community. The immense size of its vertebrae dwarfed those of any snake alive today, and the fossils provided a rare glimpse into an ecosystem where reptiles were the apex predators. These swamps were hot and humid, with temperatures far higher than today's rainforests, creating the perfect conditions for a cold-blooded giant like Titanoboa to grow to such extraordinary proportions. Titanoboa didn't just look intimidating. It was a predator unlike anything we've seen in the modern world. Fossil evidence suggests it fed on massive prehistoric fish, including relatives of today's tarpon, which could grow over 2 meters long. With its immense size and strength, Titanoboa could constrict its prey with a force so powerful it would crush bones and stop its victims' hard in moments. Imagine a predator capable of overpowering animals many times its size, gliding silently through the murky waters before striking with precision. What makes Titanoboa even more remarkable is how it rewrote the history of snakes. Before its discovery, scientists underestimated just how large snakes could grow. The extreme size of Titanoboa offered new insights into the relationship between snake size and climate. Warmer temperatures of the Paleocene allowed cold-blooded animals to grow larger than ever, and Titanoboa took full advantage of this biological opportunity. Megalodon was quite simply one of the biggest and most powerful predators to have ever lived on the planet. It was a prehistoric species of shark that lived from the early Miocene to the Pliocene, 23 to 3.6 million years ago. Megalodon's size and appearance have been hotly debated over the years. Whilst its fossilized vertebrae and skulls have been found by scientists, the most common are the teeth. From these, researchers have estimated the giant shark's size and body form. Incredibly, a megalodon tooth dwarfs that of a great white shark. A full-grown human would need to use both hands to hold one of these gigantic teeth, measuring 14 centimeters or 5.5 inches long. Equally impressive have been the fossilized megalodon vertebrae that have been found, some measuring as big as a dinner plate. Although size estimates of Megalodon have been debated over the years, their maximum length has been considered anything from 14 to 20 meters or 47 to 67 feet. In comparison, great white sharks can reach about 20 feet long, but typically average 15. Impressive reconstructions of Megalodon have shown that a full-grown human, standing upright, could fit within its jaws. Megalodon was once thought to be related to great white sharks, but fossilized evidence points to a separate lineage. Their snouts were likely more squashed than the great whites, with a less pointy tip. Due to its enormous size, it is thought that the Megalodon had extended pectoral fins to help support it in the water. These fins would be more like today's blue sharks. But what happened to the largest fish to have ever lived in our waters? What did it eat? And where did it live? Here, we ask the question, could Megalodon survive nowadays? Firstly, let's consider its diet. Would there be the same prey available today? And if so, would there be enough? We know that Megalodon dominated the oceans, and that its size has largely been estimated from its huge serrated fossilized teeth. These teeth would have enabled the shark to capture its prey. To keep an animal of its size alive, these sharks would have fed on large marine animals.
But they were also likely to be opportunistic hunters, similar to today's sharks. With a wide range of prey species on the menu, they hunted many cetaceans that ranged in size from dolphins to humpback whales. They likely ate sperm whales, bowhead whales, and those of the blue whale family, as well as seals and sea turtles. Although today's great white sharks typically attack from below, torpedoing upwards and attacking an animal's soft underbelly, Megalodon may have used its huge jaws to crunch through its prey, piercing its heart and lungs. Its feeding strategy and prey preference may have varied depending on its age, size, and global location. For example, juveniles probably ate fish and other sharks, and Megalodon populations that lived near smaller whale species probably preyed on those, rather than the larger whales found elsewhere. Teeth fragments belonging to Megalodon have been found inside fossilized whale rib bones. They have also been found lying next to predated whale remains. These findings give scientists clues about the Megalodon's diet and lifestyle. They could open their jaws wide, as much as 3.5 meters wide, displaying 276 teeth. They could likely have pierced the shells of sea turtles with a single bite. The bite force of a great white shark is predicted to be just over 18,000 newtons, but that of a Megalodon is thought to have been up to 180,000 newtons. So, would there be enough prey for Megalodon in the oceans today? Globally, whale populations have declined over the decades. Blue whale populations have dropped dramatically over the past century. Scientists believe that as few as 5,000 mature individuals may remain alive today, with up to 25,000 individuals in total. This compares to the 135,000 humpback whales and 10,000 bowhead whales. And that's not all. Some species of sea turtles are in sharp decline too. The global leatherback turtle population has declined by as much as 40% over the past 3 generations. Loggerhead sea turtles are classified as vulnerable, and other species are under threat from bycatch, water pollution, and climate change. Although there are millions of pinnipeds across the world, which include sea lions, seals, and walruses, many of these are also at risk. 10 of the 36 pinniped species are considered endangered or vulnerable. It seems that, while there may just be about enough prey to keep a small population of Megalodon alive in our oceans, these prey species are under serious threat. Many of them are on the brink of extinction. Many of their populations would not survive if a gigantic, prehistoric predator was thrown into the mix. It wouldn't be long before Megalodon overhunted what little prey was available to them. Even so, let's also take a look at the Megalodon's prehistoric habitat and the environment in which it lived. Megalodon lived in warm tropical and subtropical regions across the globe. Their fossilized teeth have been found in every continent except for Antarctica. These teeth can be found along coastlines and riverbeds. In some areas, like the east coast of North America, they are so common that people can go diving for them. The water temperatures it survived in ranged between 1 and 24 degrees Celsius, or 34 to 75 degrees Fahrenheit. There is a possibility that it practiced mesothermy. This is the ability to conserve metabolic heat, therefore keeping body temperature above that of the surrounding environment. Some of today's large sharks, like the great white, have this ability. The smaller, younger Megalodons lived in the shallower, coastal waters and those swampy lagoons. Adults preferred the deep open ocean. Evidence suggests that those living in the southern hemisphere were larger than those in the north. The oceans of today would provide the right sort of habitat for Megalodon. There are plenty of coastal regions that would offer the right temperatures for this species of shark. But today's world is very different from the Pliocene. The coast has changed dramatically, not least due to the impact of man. Could a huge apex predator survive the heavy shipping lanes, dwindling fisheries, noisy coastlines, and water pollution of today? Even in the open ocean, they would likely be affected by some form of human interference. Maybe today's world is too different from that in which the Megalodon dominated. But what was the reason for their extinction? They died off long before humans made their mark on the world. We know from fossilized evidence that the Megalodon never made it to the end of the Pliocene. In fact, it likely became extinct around 3.6 million years ago. There seem to have been a few factors that led to the Megalodon's demise. Sea temperatures cooled as the climate changed towards the end of the Pliocene. This resulted in up to a third of all marine animals becoming extinct. As the oceans dropped in temperature, Many smaller species either struggled to survive or moved away. This had a knock-on effect all the way up the food chain, right to the top. Although some of its prey may have adapted to the temperature changes and moved into the cooler seas, the Megalodon was adapted to warmer waters. It was unable to follow its prey. As well as suffering a loss in food availability, Megalodon faced another problem with climate change. Megalodon gave birth in warm, shallow coastal waters. These areas were safer for the young to avoid predation in the open water. But as ice caps formed at the poles, seawater became locked up as ice and sea levels dropped. This would have destroyed the pupping grounds that Megalodon relied upon. It was for these multiple reasons that the Megalodon became extinct. Some have questioned whether this incredible predator may still lurk in our deepest, darkest oceans today. Perhaps a small population still survives, going undetected for thousands of years. Although having a predator like a Megalodon would be an awesome, if not terrifying sight, it is almost impossible for them to be living today. We would have seen some evidence by now. We would have seen large bite marks on some of its prey that washed ashore. Or we would have found their huge teeth littering the ocean floor, not just the fossilized ones. To go undetected, Megalodon would have to survive in the deepest, open ocean on the planet. But this was a warm water species. It would not be able to inhabit the cold waters of the deep. Unfortunately, we believe the greatest predator to have ever graced our oceans would not survive today. For such a huge animal, there wouldn't be enough food or habitat left. It would face the same difficulties and threats that today's marine wildlife is facing, and, being an apex predator, it would fall the hardest of all. Pterosaurs were flying reptiles. They have often been called dinosaurs in the past, but this is untrue. They were related to dinosaurs, but weren't technically dinosaurs, as they evolved on a separate branch of the evolutionary reptile tree. After insects, they were the second group of animals to have evolved the use of powered flight, flapping their wings to propel them in the air, rather than just gliding or leaping from a height. They were a diverse group of reptiles. Some were as large as a fighter jet, and others as small as a paper airplane. Wingspans ranged from 25 centimeters, or 10 inches, to 11 meters, or 36 feet. The success of this group of animals is shown by the length of the time they existed on the planet. They spanned most of the Mesozoic era, which encompassed the Triassic, Jurassic, and Cretaceous periods from 228 to 66 million years ago. You would be forgiven for believing that today's birds descended from pterosaurs, as they shared similar behavior. However, despite living during the period and taking to the skies, modern-day birds did not descend from pterosaurs. Instead, they evolved from terrestrial, feathered dinosaurs. Today we ask the question, could pterosaurs survive nowadays? Firstly, let's look at the pterosaurs in a bit more detail to find out if they could survive on today's planet. The pterosaurs can be split into two distinct groups. The basal pterosaurs were the more primitive type of flying reptile. They were the first to appear during the late Triassic and were relatively small compared to their giant descendants. The wingspans of these smaller pterosaurs generally did not exceed 2.5 meters. These wings comprised a membrane that connected their hind legs to an extensively long fourth finger on their forelimbs. Because of this membrane, it used to be thought that they were poor at moving along the ground. However, new evidence in the form of fossilized footprints or tracks has revealed that these flying reptiles were good at walking and may have even chased after small animals along the ground when hunting for food. They walked efficiently on all fours despite their back legs being hampered by the membrane that formed their wings. They had claws which would have made them expert climbers, and it is believed that they may have spent a significant amount of time in trees when they weren't flying. These smaller basal pterosaurs had long tails and teeth inside their mouths. They were expert flyers and caught insects on the wing, as well as small vertebrates, which they plucked from the ground as they swooped down low. Some of the larger basal pterosaurs had needle-like teeth, which helped them grip onto the fish they caught from the sea. Others were specialists in eating beetles, and some behaved like today's insectivorous bats, flitting through the darkness of night and catching an array of insects in the air. Most of these primitive pterosaurs, however, had become extinct by the end of the Jurassic period, but the larger species were thriving and dominated the skies. These more advanced pterosaurs were called pterodactyloids and evolved to be very large. The largest known was called quetzalcoatlus. It stood at 3.6 meters, or 12 feet tall, and had a wingspan of 12 meters, or 40 feet. It was the largest animal ever to grace the skies. These larger pterosaurs developed toothless jaws, short tails, and well-developed crests on their heads, which they used for display purposes. The diets of these flying reptiles appeared to be enormously varied. Many of the larger specimens were thought to have been mostly piscivorous, diving into the water to catch fish. However, recent analysis on teeth microwear shows that some species primarily fed on carrion and terrestrial vertebrates. By studying the shape of the pterosaurs' beaks and the structure of their wings, scientists have been able to determine the specialized diet for some of the more advanced pterodactylids. Those with shorter, more robust wings were fish eaters and able to dive or swim underwater to catch their prey. Some were dip feeders, like today's frigate birds. Others were more like cormorants and dived into fresh water. And others, like gannets, were plunge divers, dropping from a great height and plunging below the surface of the ocean in the pursuit of fish. Other piscivorous pterosaurs included Pterodastro, which was a filter feeder like today's flamingos. It used its tiny teeth to sift out small invertebrates from the shallow water. The non-piscivorous pterosaurs were also adapted to consume a variety of different foods. Some were omnivorous and supplemented seeds and berries with insects flying through the air. Others had powerful jaws and bite forces, which allowed them to crack open mollusks or capture medium-sized dinosaurs. And some, called Ashdarchidae, were like today's ground hornbills and storks, roaming the ground for any terrestrial vertebrate that they could swallow whole. Looking at the pterosaurs' diets and feeding techniques, they are so similar to some of today's birds that it's hard to imagine them struggling to find food nowadays. Although there would inevitably be competition from today's birds that have filled those niches, we believe that based on diet alone, pterosaurs could survive nowadays. But what about the habitat and climate they were used to? The Mesozoic era, during which the pterosaurs lived, was a period of huge geological change. The supercontinent Pangaea broke up, splitting into the continents we are familiar with today. There was a huge amount of seafloor spreading, which altered the sea levels. This had a knock-on effect, changing the climate of the Earth's land masses. The deserts that once covered a large area in the center of Pangaea retreated, and greenery spread across the land. Humidity increased as the sea levels rose and surrounded more of the land. There were a few plants that we are familiar with today. The grasses only emerged towards the end of the era, and the landscape was mostly dominated by non-flowering plants, such as conifers and cycads. However, being omnivorous, carnivorous, and piscivorous, the pterosaurs would find the small vertebrates, flying insects, and fish that they used to feed on still around today. They would have been used to a much warmer climate, however. The external temperature may have been essential in their flying activities, which could mean today's lower temperatures would be prohibitive. But living nearer the equator and in some of today's hotter countries may enable them to survive. There is also the question of oxygen. Conflicting studies surround the debate regarding the atmosphere during the Mesozoic. Some suggest that there were lower levels of oxygen, whilst others suggest oxygen concentrations were higher than today. Being adapted to a higher oxygen environment would make moving to lower levels difficult to cope with. But if the reverse is true, the pterosaurs, being used to less oxygen, could thrive in the higher oxygen levels of today. So in conclusion, we believe that pterosaurs could survive today, as long as they could find their own niche in the right climate. There would be no doubt that introducing pterosaurs into today's ecosystem would cause a stir. Although many of the pterosaur species seem like they would fit into the niches occupied by today's birds, they would bring a whole other level of competition. Those relying solely on fish for their diet would, like many of today's seabirds, face dwindling fish stocks, marine pollution, and conflict with humans. The smaller, more primitive species may survive on insects like some of today's bat species, and others could hunt small vertebrates in the warmer parts of the world. So, why did pterosaurs become extinct in the first place, especially whilst the flying dinosaurs, known to us as birds, survived? Recent evidence suggests that pterosaurs were, in fact, doing quite well towards the end of the Cretaceous period. Just before the mass extinction of the dinosaurs, their numbers weren't dwindling as was first thought. Instead, they were thriving. But when the meteor hit, they too met their doom. Scientists now believe that this could have been due to their size. Although pterosaurs began their evolutionary journey as small, bird-sized reptiles, these died out before the end of the Mesozoic, and the later species grew into enormous reptiles. Even the smallest of these had wingspans over 2 meters or 6 feet. During the mass extinction, only the small animals survived. Nothing over 25 kilograms or 55 pounds made it past the Cretaceous period. Birds, in comparison to pterosaurs, were very small. Their size was likely inhibited by the presence and competition from the pterosaurs. This means that the pterosaurs inadvertently caused the birds to survive mass extinction where they themselves could not. Furthermore, birds could rely on plant life to survive, while pterosaurs needed to hunt to eat. It is incredible to think that today's birds have survived since the Mesozoic era, and even made it through the mass extinction when some of Earth's most fearsome predators could not. The short-faced bears that once roamed North America belonged to the genus Arctodus. 2 species were found on the continent during the Pleistocene: the lesser short-faced bear, Arctodus pristinus, which predominantly lived during the early Pleistocene, and the giant short-faced bear, Arctodus simus, which predominantly lived towards the end of the Pleistocene. Both species likely overlapped with each other, but Arctodus simus evolved from Arctodus pristinus. The bears were similar in appearance to today's bears, but considerably larger. The biggest was the giant short-faced bear, which could grow up to 950 kilograms, or 2,000 pounds in weight, had a shoulder height of 1.6 meters, or 5.2 feet, and when standing on its hind legs, could reach heights of 4 meters, or 13 feet. Although they are considered to have been omnivores like many of today's bears, they are thought to be the largest carnivorous land mammals that ever lived. Here, we ask the question, could short-faced bears survive nowadays? To answer this question, we need to consider the bear's habitat, climate, and diet, and compare these to what's available today. Firstly, habitat. The lesser short-faced bear, Arctodus pristinus, was largely found in today's Florida. It preferred to live in open grassland habitats that were largely dominated by longleaf pine flatwoods. As Florida's wet, forested habitat gave way to a drier, more open environment during the climatic shifts that occurred towards the middle of the Pleistocene, the lesser short-faced bears vanished. It is thought that the descendants, the giant short-faced bear, lived in a range of habitats from grasslands to tropical thorn shrub and woodland. In Mexico, it lived in an open forest dominated by low, bushy evergreen junipers. In California, the bear's habitat shifted from wetter mixed woodland, grassland, and marshes to more arid, mixed savannas as the Pleistocene continued. Most of Canada was covered in glaciers, but occasionally an ice-free corridor would emerge, allowing animals to migrate. During these times, Arctodus fossils have been found in northern Canada and Beringia, where some species such as lions, brown bears, and homotherium became locally extinct. Arctodus remained. During the Pleistocene, it seems that the short-faced bears were a highly adaptable species. They survived and thrived in a wide and diverse range of habitats, and even as the habitats and climate shifted as the Pleistocene progressed, the bears continued to occupy the same niches. Today, conditions may be different from those of the Pleistocene, but there is a chance the short-faced bears could survive in the habitats available. As the climate warmed, the glaciers that covered much of North America began to retreat, leaving behind a landscape that was shaped by glacial deposits and erosion. In the warmer, ice-free climate, forests began to expand across much of North America, replacing grasslands and other habitats. Changes in precipitation have led to changes in river systems, with some rivers shifting their courses and others drying up completely. The short-faced bears occupied habitats that are present today. Woodlands and open grasslands are still found throughout North America and would provide the sort of suitable habitat for these prehistoric bears. So, let's now consider the climate. During the last glacial maximum, About 20,000 years ago, the global temperatures were about 6 degrees Celsius cooler than they are today. The world was a drier place, with a lot of the world's water locked up in glaciers. The sea levels were lower, and rainfall was half of what it is today. This created a different climate and environment compared to today, in which short-faced bears thrived. Their thick, shaggy coats helped keep them warm in the cooler temperatures. They would have had substantial fat reserves to survive the colder climates. However, there was less seasonality back then. Unlike today, there were less obvious seasons in North America. The adaptations that short-faced bears had to keep them warm may be too much for them if they lived today. Like some of their modern-day relatives, short-faced bears could overheat easily if they exert themselves or were exposed to hotter temperatures. This may mean that short-faced bears would change their geographical location to live in more northern regions where the temperatures are cooler. Fossils of Arctodus pristinus have been found mostly in Florida, but also in Kansas, South Carolina, Maryland, Pennsylvania, and Mexico. It was most populous in the southeastern states, thereby avoiding competition with the black bears, which were largely found in the Northeast during the Pleistocene. What did the bears eat, and would they be able to find the same food today? It is largely accepted that the short-faced bear was omnivorous. It would have eaten a range of berries and plants as well as meat. The hunting strategy, however, is hotly debated. Some researchers have suggested that the long limbs of the short-faced bear were built for running speed. This gave it the name running bear. If this were true, then the animal could chase herbivores across open plains, hunting them down over long distances. But the immense size and heavy body of the bears suggest that, like today's brown bears, they weren't built for speed. They weren't agile, so were unlikely to chase after agile prey. The structure of the bear's backbone, as evidenced by fossil records, shows that they had little flexibility in the spine, and the way the vertebrae are positioned suggests that they were not quick at accelerating. Furthermore, the bears had a plantigrade gait, meaning that their entire foot was placed on the ground when walking or running. Faster predators tend to sprint on their toes, with their heels lifted off the ground. All this leads to the conclusion that the bears didn't chase their prey. A suggestion has been put forward that the prehistoric bears were scavengers. Their fossilized teeth have shown wear and tear, reminiscent of bone cracking. This could also explain their large body size, which would have been used to defend carcasses that they came across. However, the dentition of fossilized short-faced bears is not as worn as that of known scavengers, such as hyenas. The dentition, such as the broad, flat molars, and the structure of the mandibular muscles, suggests that the short-faced bears were more herbivorous than omnivorous. The plant material they consumed was typically coarse and unselectively grazed. Of course, like many modern bears, it is still assumed that short-faced bears ate meat. Whether they actively hunted the prey is a topic for debate. But tooth marks on prey such as ground sloths and proboscideans confirm that they were at least partly omnivorous. The flora and fauna of North America have changed since the Pleistocene. Indeed, the climate changes, which resulted in a huge shift in the plant species, are thought to be largely responsible for the mass extinction of the megafauna, including short-faced bears. The giant short-faced bear, Arctodus simus, fed on C3 vegetation such as leaves, stems, bark, and flowers from trees, as well as shrubs and grasses. They also consumed the prey species that browsed this vegetation, such as deer, camelids, tapir, bison, and ground sloths. Some scientists have suggested that the changing vegetation may have played a role in the extinction of some megafauna species. For example, some species may have been better adapted to the open grasslands of the Ice Age and may have struggled to compete in the new forested environments. So, could the flora found there today support short-faced bears? It's difficult to say. It depends on how adaptable the species is. There would certainly be enough vegetation to feed these immense beasts, but whether their digestive systems would be able to cope with a new, unfamiliar type of vegetation is another question. Like modern-day black and brown bears, the short-faced bear would be able to prey or scavenge upon the likes of moose or elk. They may also be able to catch and feed on fish like some of today's bears. Would there be enough prey to feed these giant bears today? Depending on their population size, there could be. In certain areas, They may compete with bears that already inhabit the ecosystem, such as North America's brown and black bears and Canada's polar bears. Interestingly, where short-faced bears lived alongside brown bears, particularly in Beringia or Alaska, the smaller, less dominant brown bears were largely herbivorous. The short-faced bears outcompeted their smaller counterparts for prime prey, consuming grazing animals and probably also fish. The same is true for today's brown and black bears. Where brown bears are absent, black bears consume more meat and fish in their diet. But when brown bears inhabit the same area, black bears are less able to fish for salmon and have much smaller territorial ranges. Fossil evidence of Arctodus is quite sparse compared to other predators that lived at the same time. As a result, it is thought that these bears lived in low population densities, which would suit them if they survived today. With an ever-shrinking habitat available to them and fewer food resources, lower population densities could serve them well in today's climate. It seems that Arctodus was an adaptable animal. From the evidence presented from fossil studies, it lived in a wide range of habitats and consumed a rich and varied diet. So why did it become extinct like the other megafauna? Arctodus survived in the Pleistocene-Holocene boundary. It was one of the last species of megafauna to become extinct during the Quaternary extinction event that removed between 30 and 40 genera from North America. Climate change caused a shift in vegetation. It led to less nutritional plant matter, which is one of the main reasons some species struggled to survive. For Arctodus, however, the dental wear and tear from the fossilized remains don't seem to suggest the genus went hungry. It is thought that short-faced bears had very low genetic diversity. Fossilized specimens found in Ohio were very closely related to specimens found in Beringia, which had been isolated for tens of thousands of years. With a low genetic diversity, the genus was more vulnerable to environmental changes. Although food shortages don't appear to be to blame for the bear's demise, changes in the nutritional quality of the vegetation, along with changes in the habitat, could have attributed to their extinction. Small population sizes and a lack of fresh genes coming into the population would have made them vulnerable to extinction. All in all, it seems that there is a possibility that short-faced bears could survive nowadays. They have a similar lifestyle to today's brown and black bears, occupying similar niches and consuming a similar omnivorous diet. However, as they were unable to adapt to the changing environment that was reminiscent of the Pleistocene-Holocene boundary, they would unlikely be able to survive in the rapidly changing world of today. With its ferocious appearance, powerful jaws, and retractable claws, Thylacoleo, also known as the marsupial lion, was the ultimate predator of the Pleistocene epoch. Its muscular body could grow up to 1.5 meters, or 4.9 feet in height, and it could weigh up to 160 kilograms, or 350 pounds. Despite its impressive size, the marsupial lion was a nimble and agile predator that could take down prey much larger than itself. Thylacoleo's retractable claws were particularly impressive, as they allowed the predator to climb up trees and ambush prey from above. Its powerful jaws could deliver a crushing bite, which was particularly useful for taking down large herbivores such as giant kangaroos and Diprotodon, a giant wombat-like marsupial. But Thylacoleo's hunting strategies and physical adaptations were not the only factors that made it such an impressive predator. It was also a highly intelligent animal, capable of adapting to changing environmental conditions and seeking out new sources of prey. It was a solitary hunter, and its social behavior was limited to mating and raising young. Thylacoleo also had an excellent sense of smell and hearing, which made it a formidable predator in the dense forests and grasslands of prehistoric Australia. However, despite its many strengths, the marsupial lion eventually went extinct around 30,000 years ago. The main cause of its extinction was the disappearance of its prey, which was likely linked to changing climatic conditions. But could Thylacoleo survive in today's world, where the climate and prey availability has changed significantly? To answer this question, we need to compare the environment in which the marsupial lions thrived to the environment they would find themselves today. We can look at their habitat and diet, as well as the global climate during the Pleistocene. We also need to consider competition Thylacoleo was subjected to, and whether the same competition exists today. Firstly, Let's look at the Thylacolio's habitat. Thylacolio was an incredibly adaptable predator, capable of thriving in a range of different habitats, from dense forests to open grasslands. But would it be able to adapt to the changing climate of today's world? During the Pleistocene epoch, Australia experienced a wide range of climatic conditions, from warm and wet to cold and dry. The marsupial lion was adapted to a relatively arid and unpredictable environment, where it had to cope with seasonal droughts and limited water sources. In today's world, however, Australia's climate has changed significantly, with temperatures rising and rainfall patterns becoming more unpredictable. Despite these changes, it is possible that Thylacolio could adapt to the new environmental conditions. Its ability to climb trees and ambush prey from above could be particularly advantageous in the dense forests and woodlands that still exist today. Additionally, Thylacolio was capable of going without water for extended periods, and its kidneys were adapted to conserve water, which could be beneficial in areas where water sources are limited. However, Thylacolio would face some significant challenges in adapting to today's climate. For one, the hotter and drier conditions would likely limit the availability of prey, particularly large herbivores. Thylacolio's preferred prey, such as giant kangaroos and Diprotodon, were adapted to the cooler and wetter conditions of the Pleistocene, and their populations have declined significantly in recent times. Thylacolio would need to adapt to new prey sources, which could be challenging, given its specialized hunting strategies and dietary requirements. Additionally, human activities such as hunting and habitat destruction have significantly impacted the populations of many native animals, further reducing the available prey for marsupial lions. While Thylacolio was a highly adaptable predator, it would face significant challenges in adapting to the changing climate and environmental conditions of today's world. Its ability to climb trees and conserve water would be advantageous, but the decline of its preferred prey and the competition from other large predators would make survival challenging. This leads us to consider the diet of Thylacolio. Thylacolio had a specialized diet that included large herbivores like giant kangaroos and Diprotodon, which were the dominant herbivores of Australia during the Pleistocene epoch. These animals were large enough to sustain a predator the size of a marsupial lion. Thylacolio's hunting strategy was to ambush its prey from above, using its powerful forelimbs to hold its victim still, while it delivered a fatal bite to the throat. This strategy requires a large and powerful animal to succeed, and it was a key factor in Thylacolio's success as a predator. However, the extinction of the megafauna of Australia, which occurred around 50,000 years ago, has limited the availability of prey species for Thylacolio. The reasons for the extinction of these animals are still debated, but human activity likely played a significant role, either through hunting or habitat destruction. As a result, many of the prey species that Thylacolio relied on for its survival no longer exist. Today, smaller herbivores like wallabies and possums still exist in Australia, but they are not large enough to sustain a predator the size of Thylacolio. In addition, Thylacolio's specialized hunting strategies would require it to be able to sneak up on its prey undetected, which could be challenging given the abundance of other predators and the increased human presence in many areas. Nonetheless, there are some potential prey species that Thylacolio could feed on in today's world. For example, feral pigs and deer have been introduced to Australia by humans and have become widespread in many areas. These animals are larger than many native herbivores and could provide a substantial meal for Thylacolio. Thylacolio could also scavenge the remains of other animals, as it was known to do during the Pleistocene epoch. However, the availability of prey would be highly dependent on the specific location and habitat where Thylacolio was living. In areas with suitable prey and habitat, Thylacolio could potentially survive by adapting its hunting strategies and diet. However, in areas where prey is scarce or competition from other predators is high, Thylacolio would face significant challenges in finding enough food to survive. Thylacolio, as an apex predator during the Pleistocene epoch, had no serious competition in Australia. However, the situation would be different in today's world. Thylacolio would have to compete with various other predators for food and resources, as well as face other threats, such as habitat destruction, introduced species, and climate change. One of Thylacolio's most significant competitors would be the dingo. which is a wild dog that was brought to Australia by humans about 4,000 years ago. Dingoes are known for their hunting skills and have preyed on various animals, including wallabies, possums, kangaroos, and feral pigs. Moreover, dingoes have the ability to adapt to different environments, from forests to deserts. Another potential threat to Thylacoleo would be large pythons found in northern Australia. These pythons are formidable predators and can hunt and kill prey, including wallabies and small kangaroos. Furthermore, pythons have a high degree of adaptability and can survive in various environments, such as forests, grasslands, and even urban areas. Apart from the competition, Thylacoleo would also face threats from humans, who have significantly altered the Australian environment since the Pleistocene epoch. Urbanization and agriculture have destroyed much of the native habitat, which has had a devastating impact on native wildlife. Moreover, humans have introduced exotic species such as feral cats and foxes, which have caused significant damage to the native ecosystem. Another serious threat to Thylacoleo is climate change, which has already started impacting Australia's wildlife. The frequency and severity of droughts, heat waves, and brush fires have made it increasingly difficult for many native species to survive. The extent of the impact on Thylacoleo would depend on the specific habitat and location it inhabited. In areas where the impact of climate change is severe, Thylacoleo would struggle to find food and water, making its survival uncertain. In conclusion, Thylacoleo was an impressive and unique predator that once ruled the Australian landscape. While Thylacoleo's hunting abilities and physical strength were impressive, it would face significant challenges in surviving in today's world. Competition from other predators, habitat destruction, introduced species, and climate change are all significant threats that Thylacoleo would have to contend with. Therefore, it is unlikely that Thylacoleo would be able to survive in today's world. Although it is fascinating to imagine this remarkable predator still roaming the Australian wilderness, the truth is that Thylacoleo has become extinct, leaving behind only fossils and a legacy of awe-inspiring ferocity. That's all for today. If you enjoyed this video, don't forget to like, subscribe, and share it with your friends. You can also leave a comment with what you would like to see in the following videos. Thanks for watching. See you next time.